So without much further ado, I want to introduce our first speaker, Benjamin Lengerich. So Benjamin, or Ben, is a faculty member in statistics and computer sciences. His research focuses on ML, AI, and generative AI, with applications in biostatistics, medical informatics, computational biology, and precision medicine. He develops context-adaptive AI to uncover disease mechanism, healthcare predictions, and guide medical decision-making. His work connects statistical models with foundation models to transform data-driven insights into actionable healthcare solutions. And his favorite restaurant in Madison, currently undecided, because he just moved here. But we'll ask him again next year.
All right. Thank you so much. Good to be here. Happy to chat. Lots of good stuff going on. So I'm looking forward to lots of discussion as we go on. Great. So as Chris alluded there, my home is statistics. I'm interested in how do we connect statistical models to foundation models like LLMs. At the punchline up front, I think that statistical models are very useful, even nowadays in the age of AI, because they help us order complexity. So once we can order complexity into modular components, either a human can analyze that, or maybe we can send it off to an LLM to do some sort of analysis, but packaging complexity into modular components makes it much, much easier to do analysis. Find surprises. Yeah. So why do we care about finding surprises, performing data analysis? Well, the truth is real world data is confusing. So when we go out, I'm interested in medical data, especially when we go out and measure real world medical data and try to find some insight from it. We fit some predictive model, maybe it's a black box model, and we don't really know what's going on under the hood, but we can predict an outcome very well. Well, the problem is that that real world data set is has arisen from real world processes. So we have biases, we have feedback loops, we have interventions in healthcare, especially, that are driving outcomes. And it turns out in healthcare, treatments actually work. So your probability of getting treated for a disease drastically changes what the risk of the disease looks like in the population. As a result, data-driven risks can look very different from underlying causality. So just fitting a blind model from real-world data to insight is very difficult. As a result, we have lots of methods of interpretable data science, where we break down this real-world complexity, split it into modular components, or some sort of components that we can wrap our minds around, that we can apply our prior knowledge to and understand and reason about. And historically, we've done this with humans in a loop, but maybe I want to ask today, can we replace the human as a data scientist with LLMs? If we think about LLMs or larger foundation models as kind of a sum of our prior knowledge, if we give them easy tasks, maybe they can actually be good at applying prior knowledge in the same way that humans can apply prior knowledge. They're less good at reasoning, but they're quite good at being a store of a large set of prior knowledge. All right, just diving into an example of why this might matter. You may have heard of something called Goodhart's law, which says when a measure becomes a target, it ceases to be a good measure. There's a very similar form of this for biomarkers, right? We might measure something in medicine and try to predict an outcome, but there's a very similar measure for of Goodhart's law that says when a biomarker is used to guide treatment decisions, the biomarker ceases to predict outcomes. This is what I was alluding to earlier, that in general, treatments actually work, so your probability of getting treated for a disease can drastically change what your risk looks like. As a result, when we look at real-world medical data, it might not look like we're expecting. So for instance, in this data set of hospitalized patients with pneumonia, we're looking at what's your likelihood of mortality? What's the likelihood of mortality of hospitalized patients with pneumonia? And here, along the horizontal axis is a biomarker called blood urea nitrogen, or BUN. And it has a very interesting and particular shape. The vertical axis is mortality odds ratio corrected for all other observable characteristics of these patients in the hospital. So it's not just correlated with something else, but even after being corrected for all other observable characteristics, we have this very strange shape where we have a very rapid rise in risk, maybe up 50%, and then it immediately hits a plateau and stops going up in risk. maybe it very slowly goes up in risk beyond that. It's also interesting that this plateau in risk, this change in slope, happens very close to the round number of about 40 mg per deciliter. If there are medical practitioners in the room, you might know better than me whether that is a common treatment threshold, but it's very suspicious to me as a data scientist, as a statistician, when real-world effects change slope at round numbers. It tells me maybe this isn't a biological causal effect, and my AI model that I want to deploy in the real world should not learn to mimic this effect. It should learn to understand that this is happening in the context of treatments and informed treatment decisions. Similarly, this is not just an isolated case. It's not that we cherry pick one feature. All sorts of medical features have this strange behavior. So here along the horizontal axis is creatinine, which can be thought about as an indicator of kidney failure. If you have very high creatinine levels, serum creatinine levels, your kidneys might be actively failing. And yet, even in this regime of active kidney failure, they have very low mortality risk in the hospital. We can link this to procedures like dialysis and continuous renal replacement therapy that are very effective. And so as a result, when we just look at the risk attributable to creatinine, it actually has an inverse correlation with, or it's an inverse effect between the creatinine and mortality, even though creatinine might be an indicator of kidney failure. So this is a surprise to us, and it tells us there's danger in our analysis of the risk real-world data, in our deployment of any models that are developed based on this data. This is not the effect of just one data set. So that was creatinine risk in a pneumonia data set that was a proprietary pneumonia data set. This is a similar picture from a ML+X data set. If you've ever heard of the ML+X data sets, they're kind of the best open standard for real-world medical data, but is broadly accessible. In the ML+X, which is the most recent version, we can see a very similar pattern of serum creatinine, where we have what we might expect as a healthy drop surrounded by some increased risk on either side. Gets up to a very high risk of mortality, over 2 odds ratio, but then immediately turns around, turns slope, and this one turns slope at 3.5 mg per deciliter. If we don't do any data science, if we just take our models and say, well, let's train the best, most predictive model, we might learn to put patients into kidney failure. The problem here is that treatments are not randomized, right? A doctor, a provider sees this high creatinine level, they decide, let's treat that, and the treatment works. There's no randomization, there's no point flip, so therefore downstream statistical analytics can't distinguish between the impact of the treatment that is associated with that high creatinine or whether the high creatinine itself is actually protective. As a result, these black box models might actually be dangerous to just blindly apply. So those were some examples, and I'm telling you that these surprises are dangerous, and that's definitely true. They come from hidden complexity, from somewhere where natural causality is bumping up against human interactions. So we have social behaviors, we have treatment decisions, we have all sorts of biases in data sets from humans. We might think about this as a data problem, that we could fix this with a better data set, right? If we actually observe treatments and we observe treatment decisions and we model that as an upstream process, maybe we can correct this. Maybe it's an experimental design problem where we're asking somewhat of the wrong question, and when we get the counter-causal answer, it's because we set up our experiment wrong. In the rest of this talk, I want to suggest maybe this is actually an opportunity where if we see counter-causal effects, this might mean something in our system in the real world could be improved. And maybe we can use the LLM to automatically find these surprises such that we then have a automated list of opportunities to go on down and improve our real world system. So applying that to this problem of creatinine and mortality, right? We have this shape that I was showing you before on the ML+X data set where there's some risk, and then it goes down to a local minimum in the healthy region, goes up to a global maximum and then starts coming back down. This with a very surprising low risk region at the very high serum creatinine level. Overlaid on top of the risk graph, I've put in the green line the Apache 2 risk calculator. So this is a particular risk calculator used in hospitals that is an additive scale, and there are other factors involved. But for the serum creatinine, we can actually see a very strong alignment between this expected risk and the real world risk up to a point. So we see there's a very similar pattern of healthy region surrounded by less healthy or risky regions up to a larger risk. But then at this increased risk, at this very elevated risk, at the highest risk in the expected risk, according to the Apache score, our risk in our real world data actually declines. What this indicates, or what this suggests to me, is that this step up in expected risk prompts differences in decisions, and we can see this based on rates of treatment like dialysis and CRRT. But it also might be somewhat of an opportunity. If we attribute this decrease in risk that appears to be countercausal to a treatment benefit, maybe we can extend that treatment benefit to a broader population. And if we take that to its most optimistic conclusion, maybe we can say that this entire region that appears to be countercausal could be flattened. There's no reason that a very extreme creatinine level should be more dangerous than a moderately higher creatinine level, everything else being equal. So maybe if we're going to apply the same care to these patients as we apply to these patients, we actually have an opportunity for increase or for improved treatment in the hospital. So that's how I see this as an opportunity, this problem of data science, of surprise finding, as an actual opportunity for real world systems. We have complicated systems, they produce complicated effects. When we find surprises in those downstream effects, that might tell us that our upstream system can be improved. So we want to do this automatically, of course. And what would it take to find surprises automatically? We need an expectation of what normal means. We need some scalable anomaly detection procedure. We need some sort of uncertainty quantification. So we propose two ways to do this. The first is using explicit statistical tests based on the assumptions I was talking about there. The second generalizes that to an LLM to ask what looks surprising to you, the LLM, versus what looks surprising to a pre-written statistical test. In general, both of these follow the same procedure. So first, we're going to estimate an interpretable machine learning model that decomposes the outcome, this complex outcome of mortality, into univariate components. Data scientists might look at the univariate components and analyze them just like we were doing. But here, we can also send those univariate components to a statistical test or to an LLM. What this looks like, we'll dive into in the next couple of slides. Yeah. So this decomposing model I'm talking about is roughly a generalized additive model, or a GAM model. And these are not new ideas. These are originally proposed by Hasty and Tibshirani 32 years ago. And the idea of a GAM is that it decomposes a complex outcome into a sum of univariate functions. So each one of these univariate functions can be visualized as just a graph. We add them up to get our predicted outcome. If we're adding in log space, that's actually multiplying. So these might be more complicated than they appear, but they can be very simply interpreted. Each component can be visualized directly as one univariate graph. So we built a package that estimates scams and then applies statistical models like this likelihood of discontinuity to automatically find some surprises in your data set. We've also built the same package does automated non-monotonicity finding in your GAM components because biological or natural causes tend to be smooth and tend to be predictable. So those are the two statistical tests that we come to based on this reasoning about what biological causality looks like. But we can be much broader we can expand this procedure by hitting an LLM to ask what looks surprising in general to you, rather than explicitly saying the shape of the graph has to match some expectation of a jump or of a non-monotonicity. Either of those we could test for, but it's much broader if we can just ask an LLM what looks surprising in this graph. For instance, you might not be able to read these labels, but these are comorbidities in the pneumonia data set. And highlighted in green are comorbidities that appear to be protective against mortality. So if you come into the hospital with pneumonia and you also have these comorbidities, you're less likely to die. These comorbidities are things like history of chest pain, asthma, being female, chronic lung disease. These all sound like very bad things, especially bad to have pneumonia with. But in real world data, if you come to the hospital, if you have a history of these comorbidities, you tend to take lung problems more seriously. So you come to the hospital more quickly, and your risk of dying from any given pneumonia is actually lower because of the patient perceived urgency. So we can reason through that, right? As humans, we can reason through that. But all we have is a couple bits of information. We have one value for each one of these comorbidities. We have an odds ratio. We have maybe a confidence bar around it. But we don't have that same curve that we were talking about in the GAM. We just have one value. And then somehow we have to apply our prior knowledge to it to say what's surprising. So it'd be nice if we could ask the LLM to do that. That's one thing that LLM should be able to do well. How are we going to do this? Well, again, revisiting the core idea of generalized additive models is that modularity leads to interpretability. So maybe with some poetic license, we might say that there's an information bottleneck that limits human understanding of complicated ideas. Maybe this is analogous to shipping, where big barges they can't pass through they can't go everywhere they need to, but they are loaded with modular crates, I think they're called 20-foot containers, something like that, that can be put onto the boat, shipped to the general port, and then taken off and shipped along the highway system. So modular components can pass through information bottlenecks that complicated outcomes can't. So as a result, either humans can look at each one of these in parallel, or maybe an LLM can. And in general, this gives us a perspective on combining statistical ML and LLMs towards automated data science. So maybe we can use statistical ML, interpretable models, to generate these modular components from data. We can do this as a compression step from data to model. The model then interfaces with the foundation model to do the analysis, but it's acting on a compressed representation that's already interpretable in the same way it would be interpretable to a human. In addition, because we can build in things like privacy-preserving models, we can have a privacy-preserving compression step of our data before hitting the LLM. So we built a package that does this with GAMs as the interpretable model, and then hits an LLM to ask about surprises and analysis of the GAM one feature at a time. So again, for univariable graphs, if it's just an X and a Y, we can encode those as a JSON format. So it's a pair of X and Ys with some confidence bounds. We can then pass that in through a prompt, in through a standard API to LLMs, and we can ask about outcomes. So here we ask, like, can we simplify this graph into a linearization of it? We've given it the graph in the JSON format, and it's okay. It's not amazing, but it's okay. We've done this is very preliminary testing on old models, 3.5 and GPT-4. They're starting to be able to do pretty well to do univariate analysis. If we can do univariate analysis, then in the GAM perspective, all we have to do is do univariate analysis many times. Right? We have each one of these components that have already been decomposed by the statistical model. We analyze each one of them individually, and then we perform hierarchical reasoning on the prizes that came back to us. We benchmarked this in a blinded study against doctors to see who could analyze real-world evidence and find more surprises in their EHR data. It turns out that right now, this is kind of an old study using GPT-4, but it turns out that right now, the doctors prefer their own anomaly finding over the LLM. But the LLM, GPT-4 does not appear to be as good as doctors, but the LLM is much more exhaustive, right? It finds almost twice as many anomalies as the doctors do. This is because doctors all tend to look at the same features to find surprises, whereas the LLM spreads its attention over all the features. There, the green is the LLM, how many surprises is it finding? The blue is the doctors, how many surprises are they finding per feature? And you can see the doctors are kind of concentrating on a smaller number of the features, whereas the LLM is spreading its focus everywhere. It doesn't get tired, so it's not conserving its effort by biasing itself to look at features that it expects to be surprising. So, of course, this is a very, very preliminary step. As I was showing there, the doctors still prefer their own explanations over the LLMs, but the LLM doesn't get tired. It can look at every single feature. It can look at 46 features and do that in, 2 minutes. As a result, I think this is a very interesting direction of research. It might be orthogonal to our handcrafted our domain experts, and we can integrate the domain experts in the loop, and they can do some sort of a false discovery rate check as well. But I think in general, this perspective of let's take data, let's compress it into interpretable models, go throughout the statistical toolkit that we've developed over years, but actually use it as a compression on data, and then use that compressed representation to interface with generative AI like LLMs and foundation models. That gives us a pathway towards automating data science. Thank you.
I'm wondering for this kind of analysis, do all the variables have to be independent, or if not, like how do you achieve that?
Yeah, so a question about the variables being independent, and the answer is no. So up to whatever you can bake into kind of a general statistical model, right? So we're saying these additive models are very good at distinguishing correlated variables, correlated effects, but there are some limitations there. And maybe in certain cases you would want to have, handcrafted, hand-designed models that you wouldn't be able to build in directly to the simple pipeline. You need something else there. But with this pipeline, since we're doing the statistical learning up front before hitting the LLM, anything that you can do by statistical learning, you can still just build into this pipeline. So far, we've used generalized additive models, GAMs, which are have some nice properties, but they don't do everything.
Yeah. Are the GAMs, are they discovering new coordinates in which the effects are independent, or are they using the coordinates that you give them?
Yeah, they're using the coordinates. So in this, I use all medical examples here, and all of the features have names that have meanings. So that's why we can pass it to an LLM and ask what's surprising about this graph, because we're giving it
interpretable because the variables are safe.
Yeah, exactly. So for an image feature, it might make less sense. I don't know how you pass a couple of pixels to an LLM and ask what's surprising about this effect, but maybe there's still something that would be generally applicable there.
The study use a JSON file to provide to the LLM.
Sorry.
You're using a JSON file.
Yeah.
But what if do they have large data?
Okay, so a question about the JSON. So to be clear, the JSON is a representation of the model. So the statistical model has already compressed the data. The size of the statistical model is invariant to the size of the data that you're training on, right? So you can make your JSON file very small, and it exactly represents the model, but the model is doing the compression of the data.
I guess, have you thought about alternatives to the foundation model? Like, are there simpler ways of unpacking the interpretable model and saying there's an anomaly, there's an anomaly?
Yeah, that's a great question. And I kind of hinted at that and never closed the loop. We did, our first attempt at this was using statistical tests. So we said within each component of the GAM, we expect the curves to be smooth and monotonic. And so let's write statistical effects. Let's write statistical tests that test for components that are jumpy or that are non-monotonic, that go up and down. So we wrote those statistical tests. They worked. They kind of put us into this aspect of real-world data looks different than you expect. TBD, how it compares exactly to the LLM.
It looks like you're converting graphs to text to feed into LLMs. How do you do that?
Yes. So converting the graph to the text, that's a domain-specific language that we wrote. It's actually very straightforward, though, because the graphs are univariate. So it's just, and they are tree-based. So that's another thing about the specific GAM model that we use. We use a tree-based GAM model. And so if you look at this graph, maybe it's a little small, but it's a constant and then some stepwise functions. You can encode each one of those steps exactly in a list of JSON coordinates. And so we wrote part of our package that does that.
Monotonicity testing, it seems like for some of the variables, you expect like a U shape.
Yeah.
How do you capture that?
Yeah. So when I say monotonicity testing, with respect to medical data, I'm cheating a little bit. It's really monotonic plus one. So there should be a basin where there's a healthy region to unhealthy regions, and then if it stops going up outside of those unhealthy regions, that's the surprising thing, right? So we kind of allow one monotonicity, one non-monotonicity, and we have a flag also that you can test only for concave or only for convex functions if you think one of those is more surprising than the other.
Right. Yes. Any interest in exploring other models, maybe that are fine-tuned, not like medical data sets? Do you think that might improve the odds?
Yeah. So definitely a lot of room to go. This is just using GPT-4, kind of old model nowadays, but it moves so fast. You use what you can. There are very interesting things, like these models have been trained on all of the medical data in the world. So if you just ask them for surprises, I did this once. I asked it for surprises in a medical data set, but forgot to include in my function call the actual data set. And they happily returned to me. They happily hallucinated surprises in medical data that have been widely published. Maybe hallucinations will go down with future models, but I think the real solution to that is use the statistical model to compress your data, and then you're interfacing in a much more simple way with the LLM. Yeah.
So you said that this system can look at a lot more variables than doctors.
Yeah.
Have you been able to show that it actually discovers some useful effects that the doctors have missed?
Yeah. So what's the point of looking at more things if you're not quite as accurate? That's one version of your question. One of the interesting takeaways that I found, is that there are surprises in zero valued effects. So if an effect comes back estimated to have no effect on the outcome, that is actually just as surprising as when something has a large effect or a negative effect. But humans tend to skip over zero effects. So for instance, there was a data set where I think it was Strider, or having wheezing breathing when you show up to the hospital. That had no effect on probability of mortality, and the doctors totally ignored that. But the LLM said, "Oh, it's surprising that we have a zero effect here, because I would expect it to indicate a more severe disease."
And next up, we have Kaiser Pister. So Kaiser is a lecturer in the computer science department at the University of Wisconsin-Madison, where he focuses on applied natural language processing and the integration of large language models in education. He has designed and taught courses such as CS 638, Large Language Models in Industry, providing students with hands-on experience in developing state-of-the-art NLP techniques. And with a background that includes founding 3 companies, 1 acquired, 1 ongoing, and 1 unsuccessful, Kaiser brings valuable business experience to his academic role. So let's all give him a warm welcome.
All right. Thank you, Chris. Let's get started. So I'm going to be talking about a specific hard problem that I have solved to some extent with AI. It actually took me a whole day of looking at this slide before I realized that the P was missing from my initial generation. I asked ChatGPT to make me an interesting intro slide for solving hard problems, I guess. I don't know. But that's pretty indicative of, the state of using AI today. These things sometimes work, often don't. But what they do is pretty neat. So a little bit more expanding on what Chris mentioned. I do teach here at UW. I have taught 2 courses. Primarily, I teach a programming language course. It's an upper division, 500 levels course for students to learn about programming and learn how to do critical thinking. I also run a small tech company called All3D, where we do generative modeling for 3D assets. So if you ever have bought something off of Walmart or many other small furniture stores, you'll see beautiful 3D or beautiful 2D product photography that was probably rendered from my product at Alt3D. I also have an incredible little daughter. This slide is a little bit for something else, so that's why she's there. But it's just such a cute photo. Outside of Alt3D and teaching, I also advise for a couple of different small startups in the AI space, where I've built and continue to build various applications of how to use GPT, how to use LLMs, how to use generative models in all sorts of different processes. One of them in particular stands out, this company, Nomad Data. They are a data company where you come to them and say, hey, I need a data set. I am currently doing medical imaging and I need a bunch of, radiology photographs so I can check my model, blah, blah, blah. They manage that and will help you find your data sets. They also want to automatically understand those data sets so that they can better offer and align solutions to providers. So they have a lot of built-in techniques that touch on what we'll be talking about today. But really what I want to focus on, and the purpose of what I want to get to today, is education. Because this is the thing that I care most about. It's educating myself, it's educating my students, it's educating my daughter. How do we learn and handle these things, and how can we augment our own education with language models? And that's how I got into the space specifically. So I started teaching at UW in fall of 22, I believe. And my course, it suffers from the internet problem, the actually problem, where, you say something in lecture. You say, yeah, okay, almost all of the time, JavaScript is a single-threaded language that does blah, 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 blah. And one of the people in the front row says, well, actually, if you're using the V8 component that handles multi-threading better, then you can get around the block. And it diverges lecture into a bit of a runaway tangent. That's not really the purpose of the lecture, the purpose of the talk. CS 538, my course, is particularly prone to this because it's about language, and it's about thinking, and it's about exploring what you could find in a programming language. And it's also all over the internet in YouTube videos. People love to comment on how you should program. There are lots of opinions in that space. And it's a really fun topic. I love it, the course. That's why I teach it. But it can lead to very closed mindsets. And people who sit in lecture feel like, oh, I don't want to ask my question because I'm worried somebody else is going to actually. I have this thought. I'm confused about the thing that's going on. But am I just not understanding it? It sounds like that person in the front row knows everything. Maybe everybody in my class knows everything. And so I worked in fall of 2022 trying to find how can I create and foster an environment in my classroom where students don't run into this looming problem. And so I worked with the LACE. It's the Learning Analytics. Somebody help me. What's the C? Does anybody know? Yeah.
Something about Center of Excellence.
Center of Excellence, I like it. And so it's an on-campus resource that helps you find ways to basically teach better. How do you educate your students and make them understand your topics? And they ran a micro grant for promoting diversity and belonging in the classroom. So I applied and said, hey, I want to run a study to say, how can I foster belonging in this classroom where there's a lot of division? Oh, some students really understand the topic, and 90% of them don't. But I don't want that small minority of 10% to overshadow the 90 who are confused. And the root of the problem here is that asking questions is engaging, and engaging is how you think. And thinking is the critical step to get to critical thinking, where you actually understand the topic. So everything that I do as an instructor, I try to get my students to do critical thinking. Is if they're actually thinking about the problem, then I think I've succeeded. I hope, at least. But this is a tricky problem, and I promise I'm getting to the AI part soon. It's one that I think deserves a lot of attention, though, how do you get students to do critical thinking? And in particular, how do you do that in a world where they think the AI is going to think for them? I ask them a question, they copy paste it into ChatGPT, and they get a perfectly reasonable answer. There was no critical thinking that happened in this step. If I ask them the same question tomorrow, they are going to have to go to ChatGPT again the next day. And there are a couple of approaches here. I think the traditional professor answer is to say, well, I'll just ask interesting enough questions. And if I just have really interesting questions, I'm going to get my students engaged because they're going to be intrigued. Which, you know, it's aspirational. I do try to ask interesting questions so that my students feel engaged and they think, oh yeah, I want to know the answer to that solution. But that's only a dream. Some questions will be better, but you're never going to get 100% coverage. One of the outcomes of the microgrant was finding some traditional methods in education using things like think, pair, share in the classroom, where you take 2 minutes, 5 minutes to have students talk to each other about potentially answering the question before you actually go through with answering the question. And Murkius Point, where you take like 5 minutes in the middle of class. It's a 75-minute lecture. So you do 30 minutes, 5 minutes, 40 minutes, and give students time to reflect on the first 30 minutes. And these things, I think, really help. I still do them today. I think they're a great practice for all educators. But the most exciting one, and bringing all of this together, what I am talking about today is, well, maybe we can fight AI with AI. You know, let's create systems that utilize language models to engage students and let students meet the class where they are, as opposed to forcing the class onto them where the class is. So here I've subtitled this Yet Another Chatbot Trained Specifically on My Course Content to Meet Students Where They Are. And that's what I built. So in the spring of 23, I put together a project where I recorded every single one of my lectures and then transcribed every single one of my lectures using Whisper AI, the OpenAI transcription model at the time. So I take all of my audio lecture recordings, transcribe those into a sequence of transcripts. This is approximately, I think, 30 hours of content. It's every lecture that I gave this semester. I then put that into a RAG pipeline, which Chris alluded to at the start of the hour, and what you would learn a lot more about at the coffee tomorrow. With the intention that anytime a student has a question, for example, they post on Piazza, they say, you know, when is the homework due? I can then go search through all of my transcripts and say, here are the 3 moments in time where I discussed in lecture when was the homework due, and provide that as related content to the question to ChatGPT and say, hey, please answer this question given the specific content of my course, and provide that answer straight back to the student. Or about 25% of the time, it would redirect the student and say, hey, sorry, I don't know the answer to that. Please consult the course staff. Here's the email. And we hooked this up to Piazza so that anybody could ask questions online and get answers. That was a cool trial. This was spring of 23. And then in fall of 23, I was approached by a company, Allen AI, who wanted to do a similar process. They wanted to put a chatbot that was trained on my course into the class website. And this time it was actually UW-Madison sanctioned. So they ran a small pilot with my course, and we are doing a second pilot this semester. Again, similar structure. They set up recordings from my lectures with transcriptions, and then whenever a student asks a question, it goes to find the relevant content and provides answers. And I've run a few different surveys over the last few semesters, polling students to see, what did they think of this experience? Was this actually helpful to them? Did they learn something more because of having an AI assistant that they could talk to? So this, just to clarify, it's a ChatGPT experience. You talk to the machine, and it tries to answer your course-related questions. So the first one here, a very simple Google Sheet chart. Has the course assistant been helpful for you in engaging or learning with CS 538 materials? And a large portion of the class says no. 31%, 32% says no. And I've actually gotten a lot of feedback from my students saying, I don't want to be talking to an AI. That's not why I'm at university. I want to be talking to you. I want to be talking to the course staff, whoever, and engaging peer-to-peer on content. So that's not a silent minority there, but an almost equivalent size group says, yes, this is directly impacting me and making me more engaged in the class. These are students who maybe didn't want to answer or ask a question in lecture that now have an easy, right in front of them solution for talking to the class. There's definitely mixed feedback, and then about a quarter of the students have not used it. This is across a sample size of about 100 students. Some more interesting findings, these are generated using ChatGPT to analyze all of the ChatGPT interactions. What are students talking about? How are they interacting with the chatbot? And a couple of the interesting ones here, the things that I personally love as an instructor, about a quarter of the questions that GPT answered were about the syllabus. When is the exam? When are homeworks due? What's my grade percent? What's the cutoff for an A? The questions that I despise in lecture because they are completely irrelevant to the content of my course. They're just the logistics of getting through the course. And if you read the syllabus, you would know them, but how many students are reading the syllabus? So if I can alleviate across this about 100 questions over the last 2 semesters where I don't have to answer the really annoying syllabus questions, that's a great load off my back. Another category here, about an 1/8 of the questions or the interactions are about generating examples. So these are times when the student says, hey, can you give me another example of that problem? Lambda calculus is really confusing. I see the homework, but that wasn't enough. Can I get more examples to work on? And I think that's a really promising area for students to go above and beyond what the course materials provide, because I can't individually provide more and more examples for every student. A concerning part of this graph is that about 30% of the interactions are, hey, what's the answer to homework 2.2? So not insignificant as far as usage goes, although they could also just go to ChatGPT to do the same thing. And then the last bit of analysis that I ran was to say, did I properly answer the question? So given a student question, does the answer that GPT properly answered the student question? Yes or no? And it was about 2/3, 1/3 of successfully answering or not successfully answering. Cases where GPT hallucinated the answer to the question, potentially just based on the foundational training that it had and not actually a course content. So again, models are not necessarily where they need to be to actually go into production learning at this point. The last part that I want to talk about is where I see this going. Because I think cool tools in the classroom are neat. Having the ability to have yet another chatbot, great. The potential that these unlock, though, is so much beyond that. And looking at the capabilities of the student-teacher relationship, we can completely reevaluate how we do education. And it stems from this quote here that I just made up and put in quotation marks so that it looks a bit more real. But when you can teach a thing, that is when you have truly learned it. I think that if you can get a student to explain to ChatGPT a concept so well that ChatGPT can then properly answer questions, that's a good demonstration of the student actually applying the content in a way that they can dictate what is supposed to happen. And that would be a sign that they've actually learned something. So I'm putting together a project here to test on my students where basically I'm trying to prime GPT to be the student, to say, you do not know anything, and let the student teach you how to do JavaScript scope evaluation, or Lambda calculus, or Haskell, whatever it is. Let the student walk you through the process of learning this. And then I will evaluate the resulting model. if the student can properly teach GPT to answer questions, then the student must have learned the content in order to teach it. So to visually show this, it'd be something, a model of some sort like this, where I, the teacher, will set some rules for ChatGPT. These are the things that you are able to understand at this point in time. You're a curious student with some knowledge of programming, but no explicit knowledge of this language task. From there, the student will effectively teach the AI, prime the context of how will this thing think about solving the problem. And GPT can go back and forth and say, okay, well, I don't understand this piece. Can you help me understand that? And the student would reply, here's X, Y, and Z, back and forth until the student feels like GPT has actually learned what it needs to learn. And then finally, what I can do is evaluate the final model to say, here's the test. Let me give the test to GPT. And if that student's version of GPT can properly answer the questions, then they have succeeded. And it goes with, that saying, the student has become the teacher. The goal is no longer to say you are a student passively sitting in a classroom and trying to absorb content. It's flipping it around to say, no, the student needs to go out and teach another student. And in order to teach another student, they must have adequately understood the concept in the first place. So this is the project that I'm working on now, trying to get set up with a way that, properly gets GPT to forget the information that I need it to forget without forgetting everything, so that it can't answer questions or ask questions. All right, thank you. That's what I was here to talk about.
There's a way to evaluate the performance of maybe
Yeah. So can we evaluate the performance of the students based on the tools? Yes, and I do, actually. I don't use it actually as part of grading, but basically every assignment that I grade in parallel, I send off to GPT and say, what would you have given this assignment? We have written assignments as well as like coding assignments. And so all the written assignments, I see, how would GPT have scored this paper? And it's not there yet. I have not given it sufficient confidence, or it has not given me sufficient confidence to say it can replace me in grading assignments, unfortunately. I wish it could.
Could I ask me, for example, do you have a track of the memory of the model that the student, they give the students? Curious about, for example, if the students will use more of the tool, by the end of the course, the class, they had a very score.
Right. So kind of getting to this chunk here. Did this chunk perform better than either of these chunks? No, this was fully anonymized. So there was no understanding of which students were choosing to use it versus which are not. Yeah. It was, we tracked history and usage, but separated from the students.
Your student teaching the AI project.
Yep.
Do you worry about the student just using GPT to do it for them? Or
Yeah, definitely. And I think that that's something we're going to have a hard time shirking at this point. There's going to be very limited scenarios where you can actually remove the capability of GPT right next to them. So we still kind of have to hope. We have to be aspirational that the students who want to learn will choose to say that this is a more interesting, it's a more fun way of learning than sitting passively in lecture, and therefore I choose to engage with it. But there will certainly still be students who say, I just want the A in the class, and GPT is the best way for me to get the A in the class, so I will do that. Yeah.
Do you request them when you evaluate, you request the prompts that they use? Like what is the language they use and the steps they took?
Yeah, so this is what I'm trying to figure out, is how exactly do I get the information from them that I want? Because it could be, what are the prompts, what are the steps that you took? And then actually I could independently evaluate just those steps effectively. Or is it a separate, excuse me, a separate format? I'm not quite sure yet. I'm still in the midst of trying to design that.
To go back to the previous question, they can also ask a GPT to create the questions.
Right.
Gemini or whoever is
right.
I do have another question. Where do you keep things So you have to make a connection between what you created as
Mm-hmm.
your set,
Mhm.
so that the regular GPT can see it.
Right.
And then where do you store it? Is it big? Is it on a local server? Is it
Yeah, so these are just
infrastructure you need?
right. Yeah, so it's all text, right? This is just the chat conversation that the student is having. So it's quite contained. It's quite compressed in terms of what's actually stored. It's kilobytes of data on my own server. So that part's the easy part. Yeah, I don't need to duplicate the model every time, thankfully.
Got two questions. So one, it sounded like 33% of the time it's giving not the correct answer to
Yeah.
students. Were you getting that in real time and correcting when
Yes. Yeah.
correct things?
Yeah. So in the cases where in this one where we see, it's not properly answering. So this was real-time feedback. It was actually a big problem though of how do I address this? Because am I supposed to post on Piazza and hope that somebody sees it? Do I wait until the next week when we have lecture again and somebody's asking? So that's actually, I don't know yet. I don't know how we're supposed to solve that problem. The ideal scenario would be meeting the student right in the moment and being like, hey, watch out, that was a bad answer. But part of the experiment here, the students were in on it. They knew that they were the guinea pigs and very much knew that some of the answers were not going to be correct, which probably influences this portion of the student population saying, well, okay, it's a 2/3 shot that I actually get good information here. So not worth my time to experiment with it. Yeah.
So the students are interacting anonymously with the chatbot. You don't know which student is asking.
Right. Right.
I feel like it would also be interesting, and I know you said that this survey was anonymous, but to stratify the data
Yeah.
I would think that the students who are already knowledgeable about the material might get to the side of the chatbot because they can discern like, oh, this is a fishy answer. And the students that are really confused might get more confused when they're getting answers.
Yeah. There were all sorts of data governance conversations that were had there that I asked for a lot and got to build a tool. And so that was kind of fun. But yeah, a lot of limits.
Hopefully not too much in the weeds, technically speaking, but I was wondering if you could comment on the RAG pipeline a little bit. Were there any specific retrieval models that worked better than others? And did the chunk size play a role, like the length of the text that you're actually retrieving as the context for the prompt? Any color in that area?
Yeah, so there were two versions of the chatbot. The first version I built myself following this architecture. And here I used a package called Sentence Transformers, which uses the BERT-based models to embed your various text pieces. I don't remember what I used for chunking, but I think it was around a paragraph or 30 seconds of text that represented each chunk. So when I was going to find the related content for a given student question, it would basically be pulling 30 seconds of content, maybe like 10 or 20 30-second pieces of content to try and answer the question. We didn't do a lot of experimentation around like the best parameters there of how many chunks, what size chunks, because then quickly I swapped to using the Allen tool instead, and it's a black box to me of what they do internally. Yeah.
Have you thought about pretending to be the chatbot and see, even if, I don't know if that, if there would be an anonymity problem or there, but, like you kind of either spy on what's happening or you are the chatbot. You actually do the answer yourself.
Yeah. I mean, that's kind of what Piazza is, although with a different expectation. People expect the answer to be a human, not a chatbot. But yeah, no, I think that would be interesting.
I mean, with the purpose of seeing how what the students are.
Right.
Do they type or do they paste? So, if they paste, the question will appear clip, plop, just like that. If they type it, you can see type, in real time.
Right. Yeah.
It just a cool idea.
Yeah, it's a fun idea.
Kind of a similar thought, I guess. Have you thought about a supervised chatbot? So every response that it gives on Piazza, it's just a draft, and you have to look at it and then approve it. It'll save you some time, but you're also not letting those errors go out into the principal world.
And kind of related to that, I was wondering, how did you brand this to the students? Did you talk about this as an AI chatbot, or was it more of like, this is a summarization tool?
No, it's very much this is an AI chatbot specifically for the course. Like anytime you would go chat with ChatGPT, consider instead using ChatGPT for 538. So it's kind of a replacement tool is what we were hoping. In some sense to get data on how are students using ChatGPT. Because if they do just come to us instead, then we'll get those logs where we can actually evaluate them.
Thinking about your students teaching the AI problem and like how fun that would be to be the student, because you've got your student, the AI is this entity that never gets tired. It's very curious, always interested in learning, very different from a lot of students that we have because we're humans, and we have the day-to-day things. So it'd be really interesting to sort of see how excited your students get about teaching based on that sort of false premise that your students are all like this.
Yeah, I think it could be a really fun model to experiment with and see like what do students start to do when they no longer have the experience of being the student and they recognize that learning is more than just the passive experience of sitting.
There's some empathy there as well. You can behind the curtain and seeing what it's like, all that stuff. Yeah.
That slide with the incorrect versus correct answers.
Yep.
Is it possible to have so simple questions with known answers to apply a numerical value and apply it as with a confidence interval and some things so that, like your question about filtering it through Piazza, only the lower confidence answers would go there.
Yeah.
Is that a feature, an attribute?
Yeah, so there is the Alan AI chatbot has lots of different steps along the way to check for confidence. I'm not intimately aware of their details there. I will also say this is, evaluation done by a chatbot and might have errors of its own where, So there's that piece as well where some of these successes are going to be false positives and failures as false negatives. But definitely getting more reflection into the system typically is going to lead to better results, which is very find those anomalies in the data that the students are generating, and then hopefully post them to the class so that everybody knows, hey, everybody seems to be confused about this one topic, and then I can go over it more, things like that.
So do you have the number, like the percentage on answers you deemed to be correct?
No, I don't. Yeah, I don't know. I looked through a lot of them, but didn't actually track this. Yes, no, yes, no, yes, no. Yeah.
So this is really exciting. Very, very exciting. I did a very preliminary version, not nearly as deeply thought out as what you've done. But I did give my exam to several frontier models. And I found that they were all worse than the average UW-Madison student. So maybe that gives a little bit of insight into your. Like on my midterm that I gave this year, the average undergrad got about an 85. The average frontier model got 80%. So they're actually very, very close.
So I have the opposite experience. My I think fall of 2022. So this would have been early ChatGPT. It was 3.5 or 4. I don't remember. Got a 93% on my first midterm, or maybe second midterm, whichever. And the student average was somewhere around a 70. Wow. Which speaks to my course. This 538 course is very widely discussed. It's a topic in computer science that a lot of people have strong opinions about and write a lot about. It tends to be a very prolific field within computer science. So I think there's a lot of training specifically on the concepts that we cover in the class.
What about filtering it, upvoting it or downvoting it for college students?
We do have that built in. So you can actually like things and dislike the responses it gets. Yeah. Yeah. And I know the one of the engineering departments is also looking at playing with Alan. And so they're trying to expand more into UW. I don't know how far they'll get, but yeah.
One last question.
You said that audio subject matter there, I would have strong opinions. So that would sound like a lot of the questions might not have the one right answer. How do you deal with that?
Yeah. No, so I think that's one of the big problems is that there aren't always one right, there isn't always one right answer. My course is very much critical thinking. This is comparative linguistics when applied to computers. It's not saying Python is better than JavaScript. It's saying Python made one choice, JavaScript made another choice. Why did they do that? What are the trade-offs? What are the benefits? And you need to actually think through that. But there is extensive write-up all across the internet on the various trade-offs between memory management this way and that way, and the performance benefits here outweigh the usability benefits there. So there's room for opinion in this field, but there's reason behind all of it. And that reason comes from the critical thinking, and students who only get to the first level to say, this is better than that, that's what I'm trying to avoid. I want students who understand why that was better, the right choice, the trade-off that was worth it.
Did this course have TAs?
One. Yeah.
I'm curious, like with answering questions on like Piazza or Discord or DMs, a lot of times that falls to TAs to kind of act like the human chatbots. So I'm curious to see if you have plans to like deploy it in a class that historically has had TAs manage those.
Yeah.
See what students prefer, I guess.
Yeah, and TAs allow for a lot more supervision of, they can approve an answer very quickly without having to then write the answer. I know Georgia Tech ran a study where they actually replaced their TA, or they had one TA that was real and one that was an AI agent, and didn't tell the students which one was which. And at the end of the semester, everybody liked the AI TA. They were so prompt with all of their replies. They replied at midnight. They replied, with all of the details that you needed them to reply with. So yeah, I think there's a lot of room for that.
And thank you, Kaiser. And once again, if you were interested in today's talks, definitely check out tomorrow's coffee event, 9 to 11 a.m. in room 11.